All right, this is an audio review of Chapter 12, Quantitative Data Analysis Using Statistics for Description and Inference. Yay! All right. So, in this chapter, we're going to talk about the process of quantitative analysis, descriptive and inferential statistics and what that means and how they're different, data processing, data inspection and modification, preliminary hypothesis testing, and multivariate testing. Excitement. All right, so like in any other chapter, the book uses examples of research in order to demonstrate some of the common features of methods that we're talking about. So the research they focus on did a survey that's similar to the GSS in that it has fixed questions that are asked over a period of time. And their survey looked at a few research questions, but the book examined one specifically, which was, does alcohol consumption affect academic performance? And so to measure this, right, to figure out a way in which to actually measure that question, they used self-reported questions on alcohol consumption, which they then combined with grade information from official college records. And the results showed that more alcohol consumed on a typical weekend night, the lower the cumulative grade point average. So this example kind of very briefly illustrates what we're going to talk about in this chapter. So how you take your research question, you analyze variables and turn it into something that can be measured and computed, and you find results, right? Such as this example that answered their question with self-reported questionnaires and combined with, GPAs to find something significant to the population that they were studying. Now to stats. All right, descriptive and inferential statistics. All right, so before we can do statistical analyses, we have to quantify the data. So we'll go through the basic steps in converting data into something you can put into SPSS, or for some terrible reason do statistically by hand. More likely you'll use SPSS. So quantitative analysis is the numerical representation and manipulation of observations for the purpose of describing and explaining the phenomena that those observations are supposed to reflect. So the process of quantitative analysis involves transforming raw data into statistics. So if we're talking about surveys, then some of that data is inherently numerical, such as age, income, right? But other data can be quantified by transforming them into categories, right? So if you took something like gender and you decided to number it to reflect the different categories that you offer on your survey, right? So 1 could be male, 2 could be female, 3 could be trans or non-binary, 4 could be declined to state, just for example, right? So some data is also, that's pretty simple, right, to make into categories, but some data is more challenging, which is why we develop a coding process, which we'll discuss in a bit. So what's the difference between descriptive and inferential statistics? Well, descriptive statistics organize and summarize data. So they make data more intelligible, and this is typically seen in tables and other figures that are used to describe the characteristics of the population that is specific to the study in question, right? So descriptive statistics are statistical computations that describe either the characteristics of a sample or the relationship among variables in a sample. So descriptive statistics merely summarize a set of sample observations, while inferential statistics estimate population characteristics and also test those hypotheses that you have. So they move beyond description of specific observations to make inferences about the larger population from which the sample observations are drawn. So this is the real deal kind of statistics that's trying to figure out sociological questions. It's called inferential because you're making inferences about some population based on the sample you created. So inferential statistics assume that data is based on random processes, right? When we talked about random sampling or random assignment. And as a result, you can apply what you found to a larger population, which is of course the ultimate goal. So in a write-up of a quantitative research paper, the tables would be presented first featuring the descriptive statistics, then followed by the inferential in relation to your specific hypotheses. All right, moving on to steps in data processing. So coding is transforming your data into numbers. So codes are developed into code books, which do serve multiple purposes, right? So first, it's this primary guide that's used in the coding process. And second, it's your guide for locating variables and interpreting codes in your data during analysis. So let's say you did a survey, right? You may need to code for those open-ended responses, and codes are developed into what we call coding schemes. So it can be compared to previous research. So the codes come from the data. So let's say you gave a survey out to Cal State Fullerton students, or at Cal State Fullerton, asking students what they believe is the biggest problem facing the college. They might write in a lot of different answers, right? It's not going to be super standardized like the questions where you have specific answers for them to choose. So they might say that, they might write in answers like tuition's too high. If you're asking what's the biggest problem facing the college, they can say it's not enough parking spaces, that the faculty are not receptive or trained, that the advisors are not available, there's not enough classes being offered, there's cockroaches in the dorms, right? Or whatever it might be, the books cost too much, or there's not enough money for financial aid. If you think about all those differing responses, you can identify some categories that are represented there. So for example, a few of the responses are related to financial concerns, such as tuition, books, financial aid comments. So if you were developing these comments into a coding scheme, you could list them in different ways. So you could list them as, things related to financial issues or not, or maybe you could even look at them as issues that are academic versus ones that are not academic. So for example, having access to advisors or getting open classes, issues with professors, things like that would all be academic issues versus not having enough parking spots, things like that. The cost, all of those things are more kind of just bureaucratic structural parts of, or non-academic ways. So again, there's many different ways to slice information. And really when it comes down to it, there's no coding scheme that's actually perfect. It's just a thoughtful process of meaningfully trying to connect the responses that you see to a set of attributes related to the variables, right? So that you're basically representing what those open answers said effectively, but connecting them to other things other people said, right? Then you move on to editing, which is pretty straightforward. You just basically check for errors and inconsistencies in the data. And of course, it's important to verify at each point. And you can deal with some of those issues in the cleaning process we'll talk about in a moment. So then third, you enter your data into a data file. And so I could talk to you all damn day about data matrices. Pretty damn boring. Basically, the way this works is like, let's imagine just in our class that you gave out a survey to 10 people. The way you'd make your data matrix is like, let's say you gave them 5 questions. You would basically have on one axis each person's specific responses. So it'd be like respondent 1, respondent 2, respondent 3, respondent 4 through 10, right? And then in the columns, you'd have the 5 specific questions you asked them, and in the actual data matrix, you'd put what their response was, right? So that's kind of the most basic way that works. Thank God we have SPSS and other things like that you can form data matrices with rows for cases and columns for variables in a much more kind of computer assisted and thankfully structured way. For this class, you're using Qualtrics, which does a lot of that for you, and thank God for that. So anyway, again, this stuff occurs automatically in computer assisted surveys and stuff like that, but not every survey is computer assisted. So anyway, code books also are related to entering data into the data file, because this is where you start defining the meanings of the codes. And as we discussed a moment ago, the code book is the guide for locating variables and interpreting those codes in your data while you're analyzing your data. So this is, this way it's all organized and categorized to prepare it for statistical analysis. And then last up there is cleaning, right, which is detecting and resolving errors in the data file. So part of this is just verification of data entries, like always good to check the information that you're entering in. We are humans, so we make mistakes, so it's always good to check. There's also different kinds of checking, right? There's wild code checking, which is a data cleaning procedure that involves checking for a range of, or things that are just out of normal, basically, out of the normal range. So, if you see each person, if you were asking them like maybe a frequency of something, and you have, everyone saying, 5 times, that's how many times I've gone to the grocery store, in the last month or something like that. And then you have someone that put, 87 times. Clearly, that's something where you want to check for things that are out of range or just kind of off to make sure that that was accurately inputted, because maybe that person actually just went 8 times. And it was like, it's kind of easy to type in 87 instead of 8. So, that's kind of one example. And then consistency checking is another way to clean. It's, a data cleaning procedure that involves checking for unreasonable patterns or responses. So like, let's say, I do a lot of research on political party affiliation and support for candidates and all that kind of boring poli-sci-ish sociology crap. So for example, if I was doing a consistency check, I could, if I'm looking through responses of people who voted in the last presidential election, and I see that one of the respondents' age is 10 years old, that doesn't make any damn sense, right? So it's things like that you would, you kind of want to go through, double check, just make sure everything makes sense. Like obviously in this country, you have to be over 18 or over to vote. So being 10 years old, that wouldn't make much sense. So just trying to find any of those outlying things or things that just kind of don't make sense to the pattern or anything else like that. Because again, sometimes they're outliers, but other times they're just mistakes that we've made while inputting the data. So you want to make sure everything's in there the way that was actually observed in the study. Otherwise, the statistical analysis won't come out correct, right? So now that all that work's done, you're ready to do it up and stats it up, right? So I find this graphic helpful to kind of explain the ways that these different types of, data or variables kind of, just a graphic representation of the differences, right? So again, we talked about this months ago, but with nominal, these are categories that have no ordering or direction, right? So these are the ones that are typically, like it says here, done with qualitative data, but of course can be quantitative in a survey or something like that. It just depends on, how you structure it. So for example, nominal variable would be gender, right? Because there's no numerical value to male or female, or in a non-binary sense, if you said, male, female, trans, declined to state, non-binary, things like that. That would be an example of a nominal category. Hair color would be another one, right? Brown, black, blonde, red, gray, maybe unicorn hair, right? Whatever it might be, ombre of some kind. A type of living accommodations could be another example, right? So, do you live in a mansion, a castle, a house, apartment, condo, trailer, motel, other, right? And another example would be religious affiliations, right? Are you, Protestant, Catholic, Jewish, Muslim, Buddhist, Mormon, atheist, right? All of those would be nominal, right? Because the categories themselves don't have any order or direction. So ordinal is different. I mean, it tells you in the word ordinal that it has ordered categories, meaning rankings, order, or scaling. So the best example, that's like a class rank, right? Like if you're first in your class, or, you graduated first in your class, or you graduated 9th in your class, or 87th in your class, right? That would be an ordinal ranking, right? Because they're basically using GPA as a way to rank all students. Socioeconomic class is another ordinal example, right? Where you basically have, it's already leveled for you, lower class, middle class, upper class, right? Or however you want to slice that. Another example could be, not to be confused with political party affiliation, but political orientation, right? Meaning that you can kind of run from one extreme to the other, from, the far right to the far left. If you said, let's say, libertarian, then conservative, then moderate, then liberal, then progressive, then radical, right? That's kind of, you're putting it in a scaled order, right? Or like even time of day, right? Is, morning, afternoon, evening, right? There's like an order to it, right? So that's all that means is, ordinal having a ranked order. So univariate analysis, right? When it comes to nominal and ordinal scale variables. So univariate analysis involves describing a case in terms of a single variable, specifically the distribution of attributes that it comprises. So for example, if marital status was measured, you could see how many of the participants were married, how many were divorced, how many are engaged, how many are single, widowed, or even always a bridesmaid but never a bride. Just kidding, that's probably not a category. The other ones are real though. And you'd have a table to show how many respondents are in each category, right? Like how many respondents responded married, single, those kind of things. So frequency distributions show the number of cases in each variable category. So sometimes it's easiest to see a frequency distribution in a graph because you can actually see how the percentages are laid out. So if you say that 52% of respondents are married, that would be an example of a frequency distribution. Well, technically, if you explained all of the percentages, that would be a frequency distribution, not just one, but related to each variable category, right? So, but I didn't want to make up fake math for the other categories I made up as well, right? So you get the idea. All right, so frequency distributions and percentage distributions pretty damn similar. Percentage distributions are based on numbers of cases in each category divided by the total number of cases. So they're calculated from the non-missing values, and they do enable comparisons across categories and distributions, which is what makes it such a useful method for expressing the relative frequency of survey responses or other data in the research. So they may, this may be an issue of how to, collapse or recode categories for further analysis. And so part of this is that, researchers can explore different questions or look at the data from slightly different populations or perspectives. And this is very meaningful, just kind of side note, because a lot of data that researchers use may be previously generated or existing data sources like GSS or Pew Research Center, things like that, right? These data sets that already exist. So you can apply your own questions using existing data, but look at it differently or focus on the relationships between specific variables in that distribution, right? So anywho, let's go on to some examples here of a frequency distribution and a percentage distribution. So first up, frequency distribution of race or ethnicity. So this is showing the number of cases in each variable category, in this case, race, ethnicity, right? So you have how many people answered what, and then you also have here on the left, the code of how they code that particular variable. So we talked about the code book and all of that kind of fun stuff, so that you basically can create a numerical representation of categories that are nominal, right? Like race. Okay, so in this one, you see how many people, or the frequency, versus in the percentage distribution, this one is similar, right, to the last one, but the percentage distribution is also looking at race or ethnicity, but specifically the percentages in each category. So instead of just telling you how many people responded that way, they're dividing it from the total number so that you have a percentage. So basically, this is a way to be able to interpret the findings. Right? So meaning, let's say you give a particular campus survey, right? But the fact that the respondents are 85% white, how does that potentially affect the outcome of the research, right? Or is that a factor to consider in how you analyze the results later on, right? So typically in, in a quantitative research paper, you're going to have a whole section which you just display the results of these either, frequency distributions or percentage distributions of your sample itself to say, okay, well, who is actually in the sample? And then later you would post those, kind of inferential statistics to look at those specific research questions, right? All right, moving on. Univariate analysis in interval and ratio scale variables. All right, so for, let's see, for univariate analysis and interval and ratio, remember, just as an example about interval and ratio variables real quick. So again, remember, each step has everything from the ones below it, but something added to it, right? So ordinal has the nominal factors of categories, but they're ordered, right? Just as interval has ordered categories as well, but the differences between the measurements, there's some sort of measured difference. That's why it's called interval, because it has values of equal intervals, right? So an example would be temperature, right? There's an equal interval between 90 degrees and 95 degrees, or between 80 and 85 degrees, right? IQ would be another interval example, or like an SAT score or something like that. And so just like that, with everything that has, the same characteristics of before, the only thing that makes ratio different is that it's an interval basically with a true zero as well, right? So something like age, right? Weight, height, income, maybe years of education, number of children you have, things like that, that can have a 0 point to it, right? So that's, I think this is just an easy graphic example to kind of remind everybody of what those categories mean and how they work. All right, back to univariate analysis of interval and ratio scale variables. So one of the things that's very important, that's, obviously commonly done to kind of analyze this stuff is central tendency. So these ones you've heard of before. I guarantee you've heard of these, right? Meaning you got your mean, your median, and your mode, right? I'm sure you've heard of that. Hopefully you have. So the mean is your average value. And again, I'm sure you've had to calculate that at some point. You just add up all the values and you divide them by the number of values. So an example would be your GPA, which represents a sort of average of your grades altogether. Even though some of them might be A's, B's, or hopefully no worse than C's, they all kind of average out to a particular GPA, right? Mode is the most frequently found value, right? So in some magical world where grades were like this, you would get a grade based on the most frequent grade you got, let's say a B+, right? It's just basically a number or category that comes up the most. And then median is the midpoint in a distribution. So this involves remembering your lower division stats class where you literally write out the numbers in a range to see what point lies in the middle. So if the ages of 5 men in a study were 16, 17, 20, 54, and 88, what's the median? 20, since that's a midpoint. I'll just save you the time of writing it out. So while, in that same observation, the mean of 16, 17, 20, 54, and 88, if you add that together, it's 195. Then you divide it by 5 for the number of cases. So the average or mean for that same data is 39. So while the median is 20, the mean is 39 for that same data, right? So this just means that one of these measures of central tendency you use needs to reflect the type of information you're examining, because they measure in different ways and they may lend better to some categories over others. So mean is often used, but if you had research with, let's say you're looking at, religious affiliation or something like that, and in your observation or responses, you have 1,000 Protestants, 275 Catholics, and 33 Jews, then you would use the mode, right? And see that the mode would be Protestants since they are the most frequent value, right? So again, it just depends on the kind of research that you're doing if you use which measure of central tendency that you use, right? Another important thing to discuss is degree of variability or dispersion. So this is the way the values are distributed around some central value, such as an average. So first for that would be range, right? Which is the difference between the lowest and highest values. So it's a very basic measure of dispersion. So again, using that age example from a minute ago with responses being 16, 17, 20, 54, and 88, the range is 16 to 88 because you go from the lowest to the highest, right? Oh, actually, I should finish that category before I move on. Another degree of variability or dispersion is standard deviation, which is the average spread of values around the mean. So this is more complicated or kind of more sophisticated measure of dispersion. It's basically an index of the amount of variability that happens or that's seen in a set of data. So a higher standard deviation just means the data is more dispersed, while smaller standard deviations means the data is more grouped together. And so the shape that you see is actually revealed by graphic presentations such as a histogram. So if you look at a larger standard deviation, it looks kind of like a wider and flatter arc, while a smaller standard deviation looks more like a peak in the normal curve, right? And again, the normal curve just describes the shape of many variables or the expectations of the null hypothesis. So here you have table 12.3 looking at, they've coded, they have the frequency and the percent here for, respondents' self-reports about how much they drank on a typical weekend night. But you see that you're looking at that, you're not necessarily seeing the dispersion, right? But if you look at the histogram on the right, you do see the actual curve itself. So you see that since if you think of the normal curve as this kind of normal shaped arc, then what do we see here? This one has a bit more of a peak to it, right? It's still a curve, but it looks a bit more grouped together, right? It has kind of more peak. So that means that there's a smaller standard deviation when it comes to people's responses about how much they drank, right? You see a couple outliers there, like almost all the way to 20, right? Which is crazy. But yeah, you got like one person being like 25 drinks. That's how many I had in a typical weekend night. And you're like, dang. But anyway, but you do see that there's, it kind of peaks in a tighter roundness, or like almost, more almost like a triangle looking, more so than the normal curve, right? So this is why histograms are so important, because they can really graphically represent the kind of dispersion that's happening within the data. All right, so you want to present your univariate data in the fullest degree of detail, but at the same time, your data has to be presented in a very manageable way. So what can inspection of univariate distributions reveal? Well, sometimes they can reveal extreme values or outliers, right? Like that guy who drank 25 drinks, right? Or things that kind of pull the distribution one way or the other. Also, another thing to look for is prevalence of missing values. So, sometimes this goes through the process when you're talking about editing and cleaning of list-wise deletion, where you eliminate all cases with a missing value. And this is okay when there's only very few missing values, but if there's a lot of missing values, that can really affect the data itself, or just, your ability to statistically analyze it. So, sometimes imputation happens where they assign values based on other information to try to deal with some of the issues of missing values, right? So data may be modified by recoding and by combining two or more variables. So you may collapse response categories. So maybe instead of a table listing very good job, poor job, very poor job, you could regroup it as good job, which is combining very good and good, and poor job, combining very poor and poor. So it may be easier to represent graphically or to illustrate your findings. So let's say you were comparing those evaluations of a good job or a poor job across multiple categories. So if it was comparing, evaluations of, let's say, across countries, like how well they think the UN is providing leadership, it makes sense to have less categories, but just to have the, good job, poor job, because you're trying to basically make quicker comparisons across countries, right? It's going to have more of an impact. So another thing to consider too is those don't knows or decline to states, which can either be omitted or it can be significant in themselves if there's a lot of respondents that select them. So there's just kind of a lot of thought process that goes into modifying the data, inspecting it, making sure it reflects what you want it to, making sure that it's accurate so that it can be analyzed, because otherwise, if you don't do this work on the front end, what you find statistically is just not going to be valid. All right, moving on to bivariate analysis of nominal and ordinal scale variables. So bivariate analysis is the analysis of two variables simultaneously to determine the empirical relationships between them. So most bivariate analysis and social research adds another element from univariate analysis, which is determining relationships between the variables themselves. So bivariate data are presented in cross-tabulations or contingency tables. So a contingency table is a format for presenting the relationship among variables as percentage distributions. So this means the values of the dependent variable are contingent, right, or rely on, hence why they call it a contingency table, or rely on the values of the independent variable. So the rows represent one variable, usually the dependent variable, and the columns represent another variable, usually the independent variable. So the cells themselves reveal the bivariate distribution, and marginal frequencies reveal univariate distributions. So what you do is, to do this, you compute percentages in the direction of the independent variable. So contingency tables are common in social research methods, but they've never really been standardized. So as long as the table is easy to read and interpret, it serves its function, right? So the function, though, of which is to compare percentages in the opposite direction of their computation. So this just means if the table is percentage down, then you read it across. If the table is percentaged across, you read it down, right? And again, this is just because they haven't standardized that. It's just kind of like, as long as it makes sense, it makes sense. So one example here would be attitude towards gun control by sex. So again, looking at a frequency distribution, right? How many people respond. So again, instead of just saying how many males or females are in the survey, right, as the descriptive statistics are doing, looking at this in a way to actually, inferentially measure what is the relationship between a question about gun control in relation to that other variable, right? In this case, sex. So you see what I mean here, that you have basically the frequencies here. You have, how many people are in favor, how many people oppose, and that itself could be a category that was recoded instead of like very favorable, favorable, or not that favorable, very unfavorable, to just be two categories, favor or oppose, right? So that gives you this breakdown. And so this one as well, the next one, same kind of deal, right? You're looking at the same question, but instead it's giving you percentage. So going back here, it tells you the question itself is, would you favor or oppose a law which would require a person to obtain a police permit before he or she could buy a gun? So we can see just from the frequencies here that, more women are in favor than men, right? And just that more people in total are in favor than oppose, right? But then when you go here, this is where you get the percentage distribution. And so this is often what people cite a lot in their research, right? Where they'll say, 79.4% of women are in favor of, that particular policy, right? Versus 66% of men. And then they can talk about why they think those, results are what they found. So that's kind of the basic crosstab. You have your category that's asking, specific to your research question about gun control. And then you have your other variable category that you're trying to measure it against, in this case, sex. All right, so the logic of hypothesis testing. So researchers use tests of statistical significance to test hypotheses, to see if variables have relationships to one another, and to see to what extent, if there is a direction of that relationship. And the tests themselves examine the likelihood that an observed relationship occurred by chance. So first you assume the null hypothesis, right? No relationship, or just complete randomness of the variables in the total population. Then you calculate the likelihood that the observed data occurred at random, right? So this is part of this chi-square test for significance of cross tabulations. So the chi-square is very frequently used test of significance in social science. It uses the null hypothesis, so it computes the distribution that would be expected if there was no relationship between the two variables. So you get a set of expected frequencies for all the cells in the contingency table. Then you can compare those expected frequencies, or this expected distribution, with the distribution of cases that are actually found in the sample data. And that way you can determine the probability that the difference is the result of sampling error and not a relationship, right? So if you found something that was, percentage-wise different, but it was only, a couple percentages off of what was expected, it might just be a sampling error issue. But let's say you found, a very significant difference, then, that's going to kind of lend more to challenging the expectations of the null hypothesis, right? So cross tabulations are really simple data tables, and they present the data, the results of the entire group of respondents, as well as the results from subgroups of survey respondents. So crosstabs let you examine relationships in the kind of way that might not be apparent when analyzing total survey responses. So a crosstab displays the joint frequency of data values based on two or more categorical variables. And the joint frequency data can be analyzed with the chi-square statistic to evaluate whether the variables are associated or independent. All right, so going to measures of association. Measures of association indicate the strength of a bivariate relationship. So the strength of a relationship is another way to think of associations. And there's various measures depending on your measurement level. So percentage difference is somewhat of a more crude measure, right? There's also the Kramer's V, right? The coefficient for 2x2 tables. So this is a measure of association between two nominal variables, giving a value between 0 and +1. And so that's based on Pearson's chi-square statistic. So it's used as a post-test to determine the strengths of association after a chi-square has already determined significance, to say, okay, so it's significant, but how strongly significant is it, right? And so crosstabs for ordinal variables reveal strength and direction of relationship. So unlike with nominal associations, crosstabs between two ordinal variables show patterns of association. And they can also reveal the direction of the relationship between the variables. So the direction of the relationship just refers to a situation in which cases with high values on the independent variable are associated with high values on the dependent variable, which is what we call a positive relationship. Or the high values on the independent variable are associated with low values on the dependent variable, which again represents a negative relationship. So percentaging shows whether lower values are associated with lower values, meaning a positive association, or with higher values, like a negative association. And so, in short, these are measures that have complicated names for the math nerds that birthed them, but thankfully programs like SPSS have incorporated these measures, so it's simply pretty much at this point, if you're using those programs, it's checking a box instead of doing a bunch of complicated calculations. All right, bivariate analysis of interval and ratio variables. Okay, so scatter plots are used to show values of two variables for each observation. So it's a visual representation of the relationship between numerical values. Basically, the data from one variable is connected to the data from another variable, and they put this in a chart. And this indicates whether there's a linear regression, or really basically if a linear regression makes sense, to do, right? So linear regression analysis selects best fitting straight lines. So the line that best describes the relationship between two ratio variables. And it has an important descriptive issue or uses, right? So basically, it's a graphic picture of the association between X and Y. And the regression equation itself is an efficient form for summarizing that association. So, yep, there it is. There's the math if you want to do it by hand. No, I'm just kidding. So A in this regression formula is the y-intercept, the point where the line crosses the y-axis. B is the slope or regression coefficient, so how much y changes for each unit increase in X. And so the residual is the difference between the observed value of the dependent variable and the value predicted by the regression equation, right? And so that's kind of, again, going to point you towards whether or not these things are valid. All right, so here we have a scatter plot of cumulative GPA and semester GPA, right? So you have a situation where you can see that they've placed the, in the scatter plot, they've placed this regression line where they think it best fits the overall results, right? So there are a couple outliers popping out there, but overall that line kind of best represents the relationship that you're looking at there. Oops, skipped right past it. This one is a scatter plot of cumulative GPA and number of drinks. So you see you have a very different kind of relationship here, right? That instead of it being very kind of collected right here around one particular line, you see a very different distribution. So again, the scatter plots or even the histograms when we're talking about descriptive statistics can be very helpful in giving kind of a visual analysis that helps explain or understand the responses in a different way. All right, so regression and correlation. So the regression equation gives the best linear prediction of the dependent variable based on the data. So it's a method of data analysis in which the relationships among variables are represented in the form of an equation, and that's called the regression equation. So the regression is how an independent variable is numerically related to the dependent variable. So part of this are regression coefficients, which indicate the magnitude of an effect. So how much changes in the dependent variable are related to the independent variable. So that's important, right? And so part of this too is how those correlation coefficients are also then used to measure the strengths of association. So this depends on the steepness of the regression line and the variation of the data around the line, right? As we saw, scatter plots can reveal very different, groupings. So correlation coefficients indicate the extent to which two variables move together, so that the regression is indicating the impact of a unit change in the variable on the estimated variable, right? So meaning how much, if you increase this particular variable, how much does that affect the other variable? So these tests of statistical significance do not indicate strengths of association. That's why you have to do other kinds of statistical tests, or those measures of association separately. All right, moving into multivariate analysis. So the logic of multivariate analysis, or the analysis of more than two variables simultaneously, is just an extension of bivariate analysis. It's examining simultaneously the effects of, multiple things. So let's say, for example, you wanted to examine simultaneously the effects of age, gender, and social class on religiosity, right? That would be a multivariate analysis. So instead of explaining the dependent variable on the basis of a single independent variable, it's explained through the use of more than one independent variable. And so that begins with theoretical models of relationships, where variables are related to each other, as well as the dependent variable. And so arrow diagrams may be used to represent models, which can be helpful because you're looking at more than two variables, and the directions of the relationships are very important to the findings. And so multivariate analysis controls for extraneous variables in bivariate relationships because it's looking at more than the relationship between two variables. So if there is a spurious correlation, it's still going to find things that are non-spurious because it's looking at more than two. All right, elaboration analysis. So this type of analysis comes from the elaboration model, or the Columbia School, for this researcher dude. Basically, it's named after that. So it aims at elaborating on empirical relationships among variables in order to interpret that relationship. And it is a model for doing multivariate analysis. So the objective is to examine the effect of third variables on a bivariate relationship. So basically the way that works is it examines an original bivariate relationship for each category of the third variable. And so part of this is creating partial tables, which reflect the partial relationship between the two variables when examined in a subset of cases that are defined by the third variable. So if you begin with a zero-order relationship, let's say between political party affiliation, because that's always where I'm going in my brain, and attitudes towards abortion, you might want to see how this varies by gender, or by age, or by race ethnicity, right? So the relationship found among different genders or racial ethnic groups would be the partial relationships, or sometimes called partials. Right? So each partial table holds extraneous variables constant. And so as a result, spurious association can occur when one extraneous variable is antecedent and bivariate associations disappear in each partial table. So that just means, another way to put that is the difference between replication and explanation. So replication is when the relationship between two variables persists when a control variable is held constant, which supports the idea that the original relationship is true, while explanation in this model is when the original relationship between the two variables is revealed to have been spurious because the relationship disappears when an antecedent test variable is introduced. So it's basically a way to kind of provide validity checks within multivariate analysis, right, using this elaboration analysis. All right, moving on to multiple regression. This is an extension of a simple linear regression, and it's used when we want to predict the value of a variable based on the value of two or more other variables. So the extension of bivariate regression to include two or more independent variables, that's what it is, right? The dependent variable is what we want to predict. So the formula, because I know you want to, do this at home, the formula for multiple regression equations is y equals a plus b sub 1, x sub 1 plus b sub 2, x sub 2 plus b sub 3, x sub 3 plus, infinity, right? Depending on how many different regressions you're trying to do, right? Or how many different variables you're looking at. So do I have it on the slide? Oh, I do. Perfect. Yay. Okay, so in this formula, a equals the y-intercept, just as before. So where it crosses the y-intercept, and the predicted value of y when all the x values are 0, right? The b sub 1 is the partial regression coefficient, which is the effect of the independent variable when all the other variables are held constant. And so nominal and ordinal variables may be included by creating dummy variables in order to use them in multiple regression equations, meaning like if you can create dummy categories that consists of two categories, like 0 and 1, right? So if you asked a question like, have you ever been married or not, right? It's kind of like if you can structure it in a yes, no, then you can pretty much create a dummy variable of, 0 for yes, 1 for no, or something like that, to create this binary that can then be input into this equation. All right, so standardized regression coefficients, what the hell is that? So basically, regression coefficients are estimates of the unknown population parameters, and they describe the relationship between a predictor variable and the response. So what's the difference between an unstandardized and standardized regression coefficient? Because, what the hell are any of these things, right? Well, an unstandardized regression coefficient indicates the change that's based on the units of measurement. So they're basically raw coefficients that are produced by that, exciting regression analysis we just talked about. And so their unstandardized coefficients represent the amount of change in a dependent variable that's due to a change of one unit in the independent variable, right? So, the book examples, the change in cumulative GPA for each drink consumed, right? But as they're raw data scores, you can't compare the coefficients, versus standardized regression coefficients are, normalized by expressing variables in units of standard deviation. So kind of what we talked about before. If you're looking at things in a more basic range way, or if you're using standard deviation as a way to measure dispersion, right? So, standardized regression coefficients are done that way so that the variances of the dependent and independent variable are 1. And so, in this example, from the book example, the change in the cumulative GPA for one standard deviation in number of drinks consumed, that in that way, you can compare the coefficients to determine the relative impact of drinking on GPA. Okay, so statistical assumptions in quantitative analysis. Inferential statistics assume the data is based on a random process. So again, the null hypothesis, right? That you're just seeing randomness and not a relationship. So linear regression analysis assumes a straight line best fits the data. They look for the line that they think best represents the relationship between the two variables, as we saw in the example. And multiple regression also assumes, right? They assume that no two variables are highly correlated, right? They also assume that the equation does not leave out important variables that would create a specification error, right? So maybe there's another variable that wasn't measured that also has a large impact on what's being seen, right? So no matter which form, each form of quantitative analysis has its own assumptions that it's important to understand so that you can kind of figure out which method or which approach best fits the context of, your own data.